next talk is Algebraic Effects Made for Logic in Cubical Agda, and the speaker is Oisin Kidney. Oisin is a PhD student at Imperial College London in Nicolas Wu's research group along with co-author Zhixuan Yang. Oisin finished undergrad in University College of Cork. This work proves a correspondence between two major approaches to handling effects. It does so in a generic way by operating on a theory of algebraic effects, formalized as syntax quotient by equations. We believe that this work opens up opportunities to combine lessons, techniques, and advantages from both styles of semantics. Please take away, Oisin.
Sure, so I'll just share. Does that look okay? Perfect. Well, thanks for the intro. So yeah, this is the talk on algebraic effects meet Hoare logic in Cubical Agda. This was a paper presented at Popple earlier this year, and it was written by myself, Zhixuan, and Nick. So we're all in the functional programming group in Imperial. Zhixuan and I are PhD students, and it's headed up by Nick. So this paper is about algebraic effects, and it's in particular a kind of a formalization of what is a well-known idea about algebraic effects, and that's this this notion of algebraic effects relating to universal algebra. This is something that's like very well studied. There are hundreds of papers on the topic, but there wasn't really a formalization available until we did ours. Or actually, we were beaten to the punch very slightly by the Agda Unimath library. But yeah, and the reason this wasn't here is because we didn't have the tools to do this kind of formalization until now. We were able to do it with Cubical Agda, a tool based on Hanatobi type theory, which gives us access to quotients. The second half of the paper also lets us combine Hoare logic with algebraic effects. Algebraic effects is kind of, they have a lot of equational reasoning tools, and there's a lot of equational reasoning in that area, but Hoare logic is kind of less used in the algebraic effects world. So in this talk, I want to give a very brief introduction to algebraic effects with a focus on how you might formalize them, a sketch of the technical contribution of the paper, and I also want to talk a little bit about using proof assistance in research. So I'm not 100% sure what the audience for this talk, kind of like what the makeup is, but I'd imagine there's a lot of people who have heard about or know a little bit about Lean, Agda, Idris, Koch, these kinds of things, and they're considering learning them or using them in their own research. And since this was a paper that was fully formalized, and all of the pain and suffering that that involves, I thought I might have some kind of advice for people who are considering using formalization in their next work. Okay, so first, algebraic effects. So algebraic effects start with universal algebra way back in the 30s. This is the study of algebraic structures like rings, semirings, and monoids, and so on. And what can you say about the syntax of expressions constructed in these structures? The correspondence between these things and computational effects was realized by Plotkin and Power. And if you want a kind of an introduction and an overview of this topic area, I would recommend the Andre Brauer paper, What is Algebraic, about algebraic effects and handlings. In fact, the first half of our paper is kind of a formalization of that tutorial. So, universal algebra. These are structures like monoids or semirings, rings, groups, whatever. These are things which have a bunch of operations and a bunch of laws that govern the interaction of these operations. So we have a monoid here. That's something that has two operations. One of them is a binary operation, and one of them is just something that has a distinguished element. And then the laws that it has is that it has a right identity, a left identity, and that binary operation is associative. Semirings then have 4 operations, a plus, a times, a 0, and a 1, and then the laws are there. So effects, on the other hand, or the way that I think about effects, are they're kind of programming language features that you can sprinkle onto an existing programming language, right? So here we have an example of Python with exception handling. So the extra little features that exception handling gives you is that you can raise an exception and you can catch an exception, right? So in this example, an exception is raised if the user gives something other than an integer, and then it's caught in that try except block. The other effect example that I have here is a non-determinism. So this is a kind of a piece of pseudo-Haskell code. It's a non-deterministic program. And the way it works is, so on the first line, we try and assign something to x. But that assignment is one of three alternatives, right? So it can either be 1, 2, or 3. On the line after that, we have an if statement, which tests x. And if x is odd, then it fails. So execution of the program stops. Otherwise, it passes. So execution just continues. And then finally, we return x. So I haven't told you the semantics for this for the second part yet. But it should be pretty easy to guess because if you fail, that branch kind of doesn't exist. That branch is useless. So what this program actually evaluates to is just 2. Okay. So we saw that universal algebra is a bunch of operations and some laws that dictate how those operations interact. But similarly, algebraic effects are also a bunch of operations or language features and some laws that dictate how they might interact. So in Python, you could imagine that you'd have a law that says the try block on the right here should evaluate to the f function call followed by the h function call, right? Because we're raising the exception x, so g should be skipped, and we should go right into the exception block, right? Or similarly, for the non-deterministic program, we could have a law that says if you have an alternative between a fail and something else, then just pick the something else. So these are equations, but they also kind of work like evaluation rules because these could be used to give us semantics to the program. So why would we bother using algebraic effects, right? The main reason is that when you constrain yourself in this way to describe effects algebraically, it's very powerful for reasoning and also for constructing effects. So for instance, on the right here, I've constructed a parser. Now, you don't have to understand the code snippets that are going on, but the fourth code snippet there is something that parses binary trees, which have simple binary trees where the leaves are either diamonds or spades, right? And this is constructed just by combining a state effect with a non-determinism effect. But because we've used all these algebraic effects that we've seen previously, because we've combined these things algebraically, we get a lot of strong reasoning guarantees about what we can do with this. So this is the stuff that's like well-known already. This is the stuff that there's a bunch of study on. What our paper did was try to formalize this in Cubical Agda, okay? So this is just a sample of kind of what the formalization looks like. I don't think I can really give a full idea in a short talk. But so every every effect, or correspondingly every algebraic theory, comes with a signature. So the signature is what operations do you have available to you. So for instance, the non-determinism effect has 2 operations available. We can fail, and we have a binary operator, right? So to specify that signature, we just give a set or a type of operations, and then we give the arity of all of those operations involved. One kind of complexity here is when we say the arity of fail is 0, we don't represent that with the number 0. We represent that with a type which has cardinality 0. So that's bottom. Or equivalently, instead of 2, we represent it with a type with cardinality 2. So that's bool. So with that signature, we then interpret that signature to give a single level of application, and multiple layered applications give a syntax tree. So these 2 code snippets you don't have to understand on the right. They're just there if anyone is familiar with Agda. The actual concrete thing that this gives you is this program from earlier can then be constructed into a syntax tree that looks something like this, right? So one way we might evaluate the syntax tree is using the laws that we had seen earlier. We could look through the syntax tree and apply them. So we'd notice that, oh, well, that's a fail branch, or see that if statement, we can evaluate it. And there's a fail branch on the left. We know that that can be pruned away, and then we'll get the resulting program, which will just be a 2. So formally, we interpret an effect, so give an actual semantics to a program by providing what's called an F algebra. So the signature for an F algebra is given on the right, but it's probably easier to understand in terms of if you can think of the universe, an algebra as something like a ring, and an interpretation of that might be integers, where we map the plus symbol to the addition on the integers, times symbol to multiplication on the integers, and so on. If we have an interpretation for an effect, so semantics for an effect, and we have a mapping for variables to the carrier type of that interpretation, we can take a syntax tree and evaluate the whole thing. Okay, so next on to theories. So that's how we formalize syntax, but we also have laws for theories. So for instance, we have for the non-determinism thing, say if we have a fail branch alternated with something else, we can just take the something else. And also that alternative choice should be idempotent. And this is where our approach differs from previous formalizations. So previous formalizations were able to talk about laws, but they weren't able to give the actual type of terms. In other words, they weren't able to say, this type corresponds to exactly all of the programs that have non-determinism with idempotency. They could say this type corresponds to all of the programs modulo the idempotent law or something like that, but they couldn't actually give the quotient type. Cubical Agda gives us these quotient types. So that first line on top there is the actual term construction. A term is a syntax tree quotiented by some relation. The ugly bit of code in the middle is the relation. So this is the thing that says 2 syntax trees are equal under some congruence laws and the laws of the theory itself. But then the result is at the bottom there. So saying that a term type actually has the equality of idempotency. And then in our model, this gives us the kind of the main result, which is we can interpret programs using F algebras that properly respect the laws of the theory involved, right? So how do we get Hoare logic into this, and how is Hoare logic involved? So this is the main kind of technical contribution of the paper, is actually the embedding of Hoare logic. It turned out to be surprisingly difficult to transfer. Kind of if you write down informally or pen and paper proofs of what you're talking about, it makes a lot of sense. But once you go into a proof assistant, it becomes very painful. So we're using this encoding that comes from a project called Haskastle. And the idea is we encode, first to encode assertions. So if you have this program up here, x equals 4, y equals 4, and then we want to assert that x equals y, the question is, how do we make a property that says this program always holds true? What is the type of propositions corresponding to that statement, right? So the first thing we do is we say that programs that contain assertions have this type, so a term of whatever the program returned originally, combined with omega, which is the type of truth values. You can think of it just as a Boolean. And the way we say all of the assertions hold true in this program is we say that program is equal to if you had just replaced all those assertions with true. Okay, so that's the kind of curly G on the right there. So all of the assertions in P hold true if P is equal to do P followed by return true. And we use this to encode Hoare logic. right? Again, so this is the encoding from Haskell. What we did was translated this into Cubical Agda, right? And the encoding takes a triple like that and encodes it as this assertion at the bottom. So this is not the whole story. The really, like the difficult part of this is actually creating that encoding. And in particular, so it's not too difficult to take the idea of an assertion and encode it, or take the idea of a Hoare triple and encode that as a program. It's very difficult to take a proof that a Hoare triple holds true and then translate that back into some property that you can use about the program. So these are just, one small page of the proofs that we had, all proving what should be pretty straightforward things. So I have about 2-3 minutes left, I think. And I wanted to talk about formalizing papers and whether or not you should do it, and whether you think it's whether it might be a good idea for your next project. So proof assistants are gaining popularity, especially with Lean, which has made huge strides in the kind of mathematical area of things. And if you're a PL researcher, you probably have the capacity to go out and learn one of these proof assistants and formalize some aspect of your work. So the question is, should you? So this paper was a good thing to formalize because formalization was the focus. It definitely made it more publishable, made people more likely to accept it. But to be clear, writing the Agda took about 10 times the time of writing the paper. And when I say the time of writing the paper, I mean every aspect of that. So in terms of discussions, it took 10 times the time of doing the diagrams, doing the preliminary research. The Agda writing was the vast majority of what was going on. So for you, why might you consider it? These are kind of some of the reasons I hear. Some people think that it'll make your results more reliable. I'm not sure I believe in that a huge amount. Like if you prove something formally, it'll certainly be more reliable than if you just prove it informally. But the effort is so unbelievably high to try and prove something formally. I think you're much better off just checking things very carefully, and you'll get quite close. It might make reviewers more likely to accept your paper. I think this is a more likely reason, but still kind of tenuous. Like a lot of reviewers don't think that formalization is very important or whatever. It's an exciting, kind of fun area, formalization, and I think it's getting bigger. So you might be able to be on the forefront of a new area of research. The formalization might incur novel research in and of itself. And from a kind of a selfish perspective, if more people start using these tools, they'll get a lot better, which will make it better for me. So the cost of formalization, there's a lot of them. You have to learn how to use one of these languages, which takes a huge amount of time. The Learn You an Agda book, which is kind of aimed at the minimum entry for Agda. So the first line of it is go first learn Haskell. Lean has pretty great resources for beginners, but in my opinion, it's probably not as good for PL research as Agda, but I haven't really used it as much recently. You do have to formalize your work, which takes a lot of time. You have to prove a lot of boring, uninteresting things that are irrelevant to your work. H levels if you're working at Cubical, termination problems, otherwise. But a lot of people should formalize. I think if your work is PL flavored, especially if it's just a bunch of type inference rules, there's a very good chance that Agda or something similar will be very good at formalizing that. If it's in kind of the more analytical spectrum, it probably won't. One thing that formalization is very good at is kind of making concrete more didactic papers. Yeah. And again, selfishly, I would quite like more people to join in with Agda because it'll make the tools better for us. the tools are currently extremely immature, yet a lot of people are using them. So I think that's good evidence that they are valuable, and I'd like more people to, to help out. Thanks.
Thanks for the great talk. Let's open up the question now. If you have any questions, please raise your hand. And if you have any questions in Zoom for virtual attendees, you can raise your hand virtually or post the questions on the chat.
Thank you for this talk. I have a comment and then a question. So as for using Lean for programming language research, indeed, there are currently some issues with using things like large, families of inductive types or nested inductive types and things like this. You can do it. It's a bit tedious. There are people working right now on libraries to make this better. So maybe in a couple months or whenever that work comes through, it might be a good alternative for programming language formalizations. And one thing that Lean does have is quotients with a judgmental equality rule, which leads me to my question. In your Cubical Agda formalization, I'm wondering, were you using any of the higher dimensional features or really just quotients and the set level stuff?
Yeah, so basically, no. Basically, we used only the quotients. We did use univalence in one place in that the type of terms in the state effect, so quotiented by the usual state laws, we were able to prove that that is isomorphic to the normal kind of Haskell representation of state, which is S to A times A. We were able to prove those two things were isomorphic, and then with univalence, we were able to translate a program that used the S to A times A into a program that used the term type. But none of the kind of fundamental results in the paper, none of the horologic translation stuff really used anything beyond quotients. So you could have done most of the main results in the paper, which is kind of Martin-Löf type theory with quotients and propositional truncation.
Hi, thanks also for the talk. It was great. I guess I have a somewhat similar question, but pushing it one layer deeper, which is you said that you relied heavily on equations and thus, or on equality and thus quotients in your formalization of the horologic, but I was wondering how it would have compared to if you had tried to use setoids and in what ways setoids would have made things worse.
So, well, I mean, in the practical sense, it would have been much more difficult to use setoids. I mean, just the normal issues that come with setoids. Having to have a custom kind of congruence law for everything that you want, and passing around a lot of extra information that's tricky to deal with. In terms of the particular kind of horologic proofs, I don't think that it would have been possible to do with setoids. I don't have a proof of that, but just kind of intuitively, a lot of the proofs relied on kind of lemmas that involve kind of universal conditions and inequality in a way that I would guess would be impossible to thread through a setoid-based implementation. So yeah, so I think just some of the technical details of the translation between horologic and effects would have been, at the very least, really, really difficult to do with setoids, if not impossible. I certainly wouldn't have attempted it with setoids.
I think I'll add one question of my own. To what extent do you think some of the pain points that you described would be easier in a theorem prover with better tactic support or automation?
Yeah, I think that would make that would help a lot of things. It depends, because some of the stuff we were doing, tactics, in my experience, are really great when you're dealing in a kind of a well understood and well known domain. You know, if you have a bunch of algebraic equations, kind of, you know, if you're doing calculations with some particular semi-ring or something like that, and you want to just automatically compute a, you know, some equality between two big expressions, it would have simplified a lot of that stuff. I worry that the stuff that we were doing would be more resistant to tactics. One place that tactics definitely would have helped is to do with H levels. So, like, if anyone has worked with Cubical Agda, or I suppose any of the other kind of hot implementations, you always find yourself having to prove random things are sets or props or something like that, even though it's quite obvious that they are a set or a prop, right? So you have some complicated record type, you're only allowed to use it in a context where it's meant to be a set. So what you have to do is you have to prove each field in the record type is a set, you have to prove their combination is a set, and all that kind of stuff. So yeah, tactics would have been really, really helpful for that. I think the big thing that Cubical Agda needs is a better interface for dealing with actual path equalities and stuff. And there have been really big improvements in that area recently, but it still needs to get better before it's painless.
I can add one more question. What features of Cubical Agda do you use that aren't present in regular Agda or Coke?
For the main results of the paper, we just use quotient types and propositional truncation. So if you just have those two things, you are able to get all of the stuff we have. For the proof that state is isomorphic to its term representation, and then using that, you do need univalence. Yeah, but those are the only kind of extra things that we use. We don't use any higher homotopy types. We don't use any groupoids or anything like that. It's really just the quotients.
If there's any other question, thanks again, Oisin.